Thank you. And so I guess the first thing is I have to let you know, why am I qualified to speak about the history of soil testing? And part of it's my gray hair. I've been around a while. So I grew up on a farm not too far from here. It's in Farmer City, which is a great place if you're in agriculture to come from Farmer City. After I went to the University of Illinois to get my BS, and after that I was in the fertilizer business. So I sold fertilizer and chemicals directly to farmers. So I have a lot of experience with nutrient management, a lot of soil testing is my background. After a while I got to the point where I had a lot of questions. I ended up going back and getting a master's from the University of Illinois, and then I went over there and I worked on a PhD for a while, but I never completed it. But in the process of that, I learned a lot about soil fertility and a lot about the history of soil fertility. There's a lot of things that we do, and my question is always, why do we do it that way? Where did that come from? How did we get there? And I think it's really important that you know those things in order to be able to figure out where we're going to go, how we improve, how we get better. So I think, this is my presentation. I just get to tell stories. And so I don't have a lot of data. I have a lot of pictures. And I welcome questions at any time, but if we're going to do it on the panel, that's fine. But there we go. So, one reason I'm somewhat qualified to talk about soil fertility is because I've done it. We have our company. We do a lot of contract research, but we also have a lab. We do nitrogen soil testing in our lab. I looked at doing all the soil testing, all the nutrients, and we have a lot of good labs in Illinois. So we have a good network of labs. They do very inexpensive work, and so I never thought that it made sense for me to do it myself. So I always used other labs for the routine soil testing that we did. But I had experience. I spent a lot of time trying to figure out if we wanted to do that ourselves or not. So we'll talk about how soil testing, what's the current state of soil testing right now, and some of the new things that are going on, where they're going, and that the history of it kind of informs us on where things are going. Currently the soil testing, we've been doing soil testing the same way for a long time. I mean, Illinois is really kind of one of the places where soil testing really took off, and I'll show you something from that a little later. But it's pretty simple. I showed the previous slide was where we're pulling the soil sample, and then you dry the sample and you grind it up, right? Then you take a scoop of soil, 1 gram or 2 gram scoop, whatever size it fits the analysis, and you add extractant to it, and for so long, you shake it, you filter it, then you put it in, then you analyze it. And so this is a ICP, inductively coupled plasma. And that's kind of you can get from the extractant, the extractant that we use commonly, we use like a malic 3 extractant. And that's kind of a universal extractant. And I'll go in and talk a little bit about when we started using that and why we started using that. But these ICPs are very expensive machines, but they'll analyze all the nutrients. So that's kind of a summary of how we've been doing soil testing for a while. We've been doing that quite a while that way. There's some new things on the horizon, and we've been working with a company, Precision Planting. They're based here in Illinois, and they've developed their own soil testing laboratory, and it's really a pretty cool piece of equipment. It's all automated, so you take a lot of the human element out of doing the soil testing. So the orange part on the right, those are the racks where you put these tubes in. And I'll show you a picture of one of those. But after you put the tubes in there, and you press go, you don't do anything else. You get the results come out the other end, basically. They come back to your computer and you can see what's going on. So that's kind of I think that's where soil testing is going. The equipment is really kind of pretty cool. On the right side there, that's where the soil comes in, pushes it out of the tube, adds water, it mixes it up. It uses the whole tube of soil. When it does it instead of using a scoop like we do in soil, a 2-gram scoop. It uses the whole sample, and it does it by mass. So we're measuring very precisely how much soil is going into the analysis. So that's a huge improvement in kind of where soil testing is going. These 3 units on the left here, the first one is where they're doing the phosphorus analysis. The second one, they're doing pH analysis. And the third one, they're doing potassium, magnesium, and calcium analysis in there. So, and then they have another one to the right there where they're going to add future analysis to the process. But it's all very temperature controlled. Does exact measurement. It's really cool to watch. And if anybody wants to see one of these and you can come to Farmer City and come to our lab, and I'll show you through it. But I think this is something that we're going to see more of this automation. Even all the other soil labs are starting to automate more of their processes, to take the human element out of it a little bit. So I think this is kind of the direction things are going. So there's one of those tubes that I was talking about that we just slide into the rack and it automatically does it. This device down here is you take the soil, all the soil you pull from your bucket, you put it in this, it mixes it up, and then you pour it in this other, and you pack it in the tube. And so when you pack it in the tube, you don't have to write anything on the tube or anything, because it uses the GPS to locate the tube and writes electronically to the tube. So when you slide it in the machine, it can read that exactly where it came from, and then it ends up on you get a map on your computer of where all the samples are. When they get pulled, they've been pulled, and when they've been analyzed, they've been analyzed. It's pretty interesting system. But really, that's not what I'm here to talk about today. I'm here to talk about the past. And so this is a picture of the farm from the farm I grew up on. This 10-year-old boy right there, that's my dad. And so I'll come back to this field a little bit and talk about what was happening in the 1930s, because that's really important to our soil testing today, because a lot of the things that we're doing today are kind of based in the 1930s and 1940s. There were a lot of developments, and we're still using some of those things today, and maybe we shouldn't be, and maybe we should, but it's important that we know where things come from. So there's been a lot of interest in fertilizer. I mean, you go back to the Romans, and they had a god of fertilizer or manure. And so I thought that was interesting that it even had its own god. But also, if you go back to the Bible, there's a parable in the Bible. A man had planted a fig tree in his plantation, in his vineyard, and he came and he looked for fruit on it. And the person the vine dresser, he said, okay, let's put some fertilizer here. Let's put manure here, and then next year we'll come and see if we have figs on that tree. And so I thought, you know, this is a conversation that I could see being between a modern farmer and his landlord, right? The landlord saying, this isn't as productive. I think this could be more productive than it is now. And the farmer says, well, okay, let's put some fertilizer on it and see how it goes, right? So we're going to change our fertilizer program. We're going to do something different. We're going to improve what we're doing. And then we'll come in and see if we have more figs, more corn, more whatever it is. So, you know, it's not a new story. We've been working to grow crops for a long time and looking to improve how we grow crops for a long time. So this slide's probably got the most words on it of any slide I'm going to show today. But it's the first 12,000 years of fertilizer history. So there's a lot of years put into there. But, you know, 8,000 to 10,000 years ago, you know, they started domesticating plants and animals. You know, a lot of the history, you know, you got to come a long time before we have really written or documented history of what's going on in fertilizer. So some of these people up here I'll start talking about. But if you look at that, there's a lot of things that happened in the 1600s and 1700s and 1800s, you know, that we're really building. It was really some of the foundational things in agriculture. We started discovering different elements, and you know, the way that these guys figured these things out is sometimes just very interesting stories, and so we'll talk about a few of those. But you know, like I said, we've been interested in fertilizer. The Romans had a god and goddess of agriculture, you know, Ceres and Saturn, and then there's our Roman god of manure, also the pictures there. So they've been thinking about this for a long time. So one of the guys that's on that slide was a hydraulic engineer. But he was far ahead of his time because he said manure is carried to the field for the purpose of restoring the latter part of what had been removed. Proceeding thus, you will restore the soil, the same substances that have been removed by previous crops and by which following crops will regain their advantage. And when I see a statement like that, I think of soil health. I think of what people are talking about on soil health, and that's kind of what I think he's talking about there. We need to replace the things that have been removed from the soil. And I think John Jones is going to speak about that also today. So we're going to talk about removals of nutrients from the soil. But back in the 1500s, they were talking about that also. Here's another very interesting experiment where they were trying to figure out what's going on. How are we trying to? How do these plants grow? What's going on? And it's Van Helmont's pot experiment, and it was a pretty simple experiment. He took 200 pounds of soil. He put a plant in it. It was a 5-pound plant. They weighed it. The only thing that was added over these 5 years of the study was water. And at the end of the 5 year, they had a plant that weighed 169 pounds. So it increased biomass by 164 pounds. And the soil, they weighed the soil also, and it was only 2 ounces less than it started at. And Van Helmont said that was he contributed that to experimental error, right? So nothing came from that was within their ability to measure. So where did all that biomass come from? Well, of course it came from the water, right? That's the only thing that was added. So, I mean, today we all know about photosynthesis and the CO2 that the plants take up. But back then, they didn't know that. And so, the conclusion he made was wrong. Van Helmont did another experiment that was also very interesting. He took, I think it was 6 pounds of charcoal, oak charcoal, and he burnt it. And after burning it, he ended up with, I think it was a few ounces of ash that was left. And he said that it ended up as what burned up ended up as gas, and then what you had left was was some of the elements that were in there that wasn't gas. So he knew that there was a gas phase and a solid phase of that. But then he goes back to this. For all of his life, he contended that it was the water that contributed to that, because they didn't know about CO2 yet. So now we're moving forward a little bit. We're in the 1600s. And Jethro Tull. And so I always thought this is interesting because there was the 70s rock group that was named after him. But he wrote, his famous essay was Horse Hoeing Husbandry. And his contention was that by stirring the soil, by doing cultivation, that you released nutrients from the soil. So it wasn't about, he was not an advocate of fertilizer or manures. He said you just stir the soil and that's going to give you what you need. He was also the person that invented the first grain drill, basically. So the early things that he did, the grain drills were developed off of that. Henning Brandt. So we're up to 1669. And so you all heard about alchemists. Well, this guy, Henning Brandt, he was trying to figure out how to turn base metals into gold. I think there was a lot of chemists, they spent a lot of time trying to do that. I don't know that anybody succeeded in doing that yet, but so he collected large quantities of human urine, believing it contained precious metals. And I thought that's kind of interesting. I don't know where that came from. But then he fermented it into a thick paste, and I said, man, his lab must have smelled really good. And he ended up with a white waxy substance which glowed in the dark and ignited in the air. And so that was, he named it phosphorus, which is light bearer. So now we're moving up. We're up into the 1800s, and Sir Humphrey Davy, British biochemist or British chemist, he's the one that discovered potassium. So he was the first one to isolate potassium. He used electrolysis to isolate potassium. He also isolated sodium by that method. So, we knew they named it was potassium, but potash. Everybody calls it potash, and because when you burned wood, that was the method they had of isolating that potash, and then he refined it through electrolysis is what he did. So here we're back in the 1700s. Daniel Rutherford, his experiment, he used mice, so he's really making advancements there. He placed a mouse in a closed jar until it died, and then he burned a candle and phosphorus in the remaining air, noting that the process had stopped because there wasn't any oxygen left in there. But the gas itself didn't support life or combust. So he knew there was a gas in there, but he didn't know what it was. He removed the carbon dioxide, so by 1772 they'd figured out carbon dioxide. And it left behind a distinct non-reactive gas. And he called it noxious air. So I thought that was interesting. It wasn't until 1790 that Jean-Antoine Claude Capel named it nitrogen. So the history of soil fertility, I think there were people in there that some of these guys are really heroes because of the work they did and how they did the work, how they figured things out over the time. We also have some people that I would say are kind of villains, and sometimes they're both. Justus von Liebig was a pioneering German chemist, and he wrote and lectured extensively about mineral nutrition of plants. He used laboratory methods to teach chemistry and was regarded as a great educator. He was held in such high esteem that few dared question his pronouncement about mineral nutrition. So, esteemed scientist, but basically whatever he said, everybody believed, and sometimes that inhibits progress. But so just about everybody, a lot of people in here will know this, Liebig's law of the minimum. They've heard of Liebig's law of the minimum. But how many people have ever heard of Carl Sprinkle and Sprinkle's law of the minimum? We have one hand. And, but it was actually Carl Sprinkle that developed the theory of the minimum. He did it before Liebig published. He actually published a paper on this, but he published it in German, and nobody read it. Liebig read the paper, published his in English, and everybody read it, and everybody contributed those theories to Liebig. And I think that Liebig just had a better publicist, and you know, I don't know, poor Carl here, he needs a makeover, I think, so. But he, you know, I think this is one of those cases where Liebig got all the credit. And I found this interesting quote about Liebig. You know, it said he was held in high esteem by everybody. Well, obviously, maybe not everybody. I thought this was interesting. Mr. Justus Liebig is no doubt a very clever gentleman and a most profound chemist. But in our opinion, he knows as much of agriculture as a horse that plows the ground. And there is not an old man that stands between the stilts of a plow in Virginia that cannot tell him facts totally at variance with his finest spun theories. And so, this comes back to, here we have a farmer that's saying, okay, I know this is what the theory is, but I've seen things that are different than that. And I think there's a lot of things that, you know, that's a good learning point. I mean, there's always things that that we see that don't work like we've been taught they were. And I've seen a lot of those things in my career. I remember a number of times where I thought, you know, I did things in the field or had things going on in the field, and it's like, that didn't turn out the way I thought it would. And so then, over time, I've learned that it's a learning opportunity. There's things that you can learn. And so I think that we always have to question authority and look at how they came about, what they got. So now I'm going to start talking a little bit more about where we got to soil testing and some of the how the modern soil testing, where we came about some of those things. So here we're up into the early 1900s. I think it was 1909 that SPL, they call him SPL Sorensen in a lot of the publications, but in 1909 he developed the scale that we use for pH. And so it goes from, you know, from 0, which is highly acidic, to 12, which is, or 14, which is highly alkaline. He was a Danish scientist that developed this. And based on that, we have Arnold Beckman. And I don't know if any of you know the Beckman name. At the University of Illinois, there's the Beckman Institute. It's an engineering building, and it's named for him. He was from Cullum, Illinois. He went to the University of Illinois for his bachelor's, maybe his master's, but he went to California to get his PhD, and he was working out there, and one of his colleagues from Illinois that he'd gone to school with called him up and said, we need a way to measure acidity in lemons. And so in California, he had gotten some experience with electronics, with the cathode ray tubes. And he said, well, I think we can build something to do that. And so he built the first pH meter. And the guy that he built it for said, well, I'll take 2 of those, build me 2 of those. And so he got the idea that maybe there's a market for these. Maybe I should start building these and selling them to laboratories. And this was during the Depression, and they said, somebody advised him, he said, no, you shouldn't do, it's a terrible time to do that. There wouldn't be enough market for this. But in the first year, he built like 195 of these, sold 195 of these, and then the second year he sold 440 of them. And so, you know, he was off to the races and saying, oh, I can do that. And then he also built some spectrometers and other things. And so the company, you know, became Beckman Coulter, and they became one of the big companies building a lot of electronic devices in the early 1900s. But many of you have seen this chart that's on the left talking about how pH affects soil fertility, right? How much the nutrients, how available nutrients are at different nutrients are available at different pHs. And so the chart from the right is from 1935. I think it came out of Virginia Tech. But if you look at that, there's some things that are similar, but there's a lot of things that are different. So over time, I think our understanding of this has changed. I think it's still there's a lot of opinion in this chart. I don't know where the science comes from, but I think it does a pretty good job of capturing the differences as we change pH. So now we get to talk about nitrogen. And so many of you heard about the Haber-Bosch process, and Fritz Haber won a Nobel Prize in 1918 for nitrogen synthesis. And so you can see a simple device that he set up to do that with. It was later, the other name, Haber-Bosch, is what you always hear. And Bosch is the one that maybe industrialized it, and I'll show a slide on that in a moment. But Fritz Haber was a very interesting person, very complex person. That process of being able to create synthetic nitrogen is attributed to saving millions of people in the world from starvation. If we didn't have the nitrogen that had been processed, has been available through this Haber-Bosch process, we wouldn't be able to support the population on the earth that we have today. But he also was considered the father of chemical warfare, and he was a Jewish scientist, but he worked during World War I, he was working for the government, and he was very loyal to the Kaiser and everything. And so he developed some of the early chemical weapons. And then as Hitler took over, he was a loyal German and wanted to support the Nazi Party, but the Nazi Party wouldn't have him at all. So he came to work at his laboratory one day, and they said, no, we don't allow Jews in here, even though it was his laboratory and everything. So he left Germany, went to Switzerland after that. So he has, he's one of these complex people. He did good things, and he did some things that are considered pretty, the development of some of the poison gases. So anytime I think about poison gases in World War I, my grandfather, who was he was a mail carrier right here in Bloomington, and he was a World War I veteran. He fought in France. He was with a machine gun unit in France in World War I, and he got gassed in the trenches in France. And so this story about the poison gas comes home pretty quick to me. He ended up dying of lung cancer, and probably had something to do with being gassed in World War II. Also, as a soldier and stuff, he also smoked too, all his life too. So those two things, I don't know which one it was, but they probably both contributed to his death. But Fritz Haber was the person that created the process to make synthetic nitrogen. But really, it was Carl Bosch, a chemist at BASF, and it was BASF, that company that was there at that time, that really industrialized the process and got that going. So, so it wasn't all his doing. I found some of these slides, from World War I, that show some of the poison gases and everything. And I thought this quote was pretty interesting, that Fritz Haber was a terrible person who actually saved half of humanity. Some people say, half from this reactive nitrogen. 2 out of 5 people I've seen that number used. But there's a lot of nitrogen that's been created in this world that we didn't have before. Since World War II, we've increased 57x at least, and that's only stopping in the mid 2010 or 15. But if you look at the amount of reactive nitrogen that we have in the world today, it's an incredible amount. And 99% of the N that's produced today is from the Haber-Bosch synthesis. It's not from natural processes. So, and that in itself causes problems in the environment. So it's one of these things that we have to look at how we can better use that nitrogen. I think we have a lot of opportunity to improve how we use nitrogen in our crops. So, but I'm not going to talk about that right now. So here we're moving forward. Now we're getting up into the 1900s. And Norman Borlaug, he's one of these guys that if you haven't heard about or read about, you should, because he was this wonderful guy. He knew a lot of adversity in his life. He came from a very poor family. He was from near Cedar Falls, Iowa. Cresco, Iowa, I think is where he was from. He hitchhiked his way to the University of Minnesota. And after high school, he worked on a farm. And he said his his academic skills lapsed during the time he worked on the farm. And so when he took his entrance exam for the University of Minnesota, he failed. Fortunately, there was somebody there that says, hey, we have this new program. It's kind of a bridge program where you can come in and take classes to get your to a point where you can pass that. So he did that. He worked, I think, either a full-time job or a couple part-time jobs while he was, the whole time he was going to school. But he was fortunate to have some really good mentors that took him along. And, you know, if you don't know what he's considered the father of the Green Revolution. He did a lot of breeding of wheat. And a lot of his work he did in Mexico. He did a lot of work in India. But the modern wheat varieties, the modern wheat that we have today, you know, a lot of it's attributed to the work that he had done, the work that he and the people that he trained had done. You know, when we start talking about the Green Revolution, you know, it's when fertilizers were a big part of the Green Revolution. Without fertilizers, you know, the nitrogen, the phosphorus fertilizers, the potash fertilizers, we wouldn't be able to produce the amount of food that we do in this world. So here we have, you know, there's a potash mine on the left here, and then a phosphate strip mine on the right. And so those fertilizers have become very important to our agricultural production systems. And so it's part of our nutrient management cycle. So we're here today, we're talking about soil sampling and fertilizers. But it's all part of this system of managing those nutrients for the farm. And so it's always about how we can get better at that. And really, we got to go back to soil testing is assessment of fertilizer needs. So we wouldn't there's no reason to take soil tests other than to manage the nutrients in our soil, manage and nutrients in our crops. But one of the things I think it's important is to kind of talk about how a soil test works. And so Roger Bray, and I'll talk more about Roger Bray as we go forward because he invented some of the tests that we use today. He also wrote a paper in 1948 that talked about how does a soil test work? What does it need to do? And a soil test needs to reflect the forms that are available to the plant during the growing season. The procedure must be reasonably accurate and timely enough that you can get it done so you can get the results and make decisions based on that. So the bottom one here, the amounts of the nutrients extracted must be correlated with the growth and response of each crop to that nutrient under various conditions. And so, you know, what that means is that if the soil test doesn't relate to a response in that crop, it's not doing us any good. The closer it relates to the response to that nutrient in the crop, the better it is, right? And so that's one of the big opportunities that we have. We have opportunity to do a better job and we need to look at that response data is kind of where we're doing. And Dr. Jones is going to talk about that, I believe, today. So here's, you know, I said I'd talk more about Roger Bray. He co-developed the Bray-Kurtz P1 and P2 tests. So he was these tests for phosphorus that were developed, and they were developed in the mid-1940s, or they were published in the mid-1940s. They probably developed earlier than that. This is the type of device that they used to measure. So it was they did the extractant, and it was a colorimetric test that as you had more phosphorus in that soil sample, you had a different color. It was, and this meter here was what they used at that time in the 1950s to measure that. And on the top there, you can't really see it very good, but there's just a dial in there that moves as that meter, the light passes through it, and it sees the different colors that are being developed from the reagents that are in that test. So that's where we started with the Bray P1, and we've gone a long ways from that. I found this article in Prairie Farmer from 1951, and the guy on the right there is Toby Kurtz, who was the co-developer of the P1 test. He was a grad student that helped develop that. And he went on to be a professor of soil chemistry at the University of Illinois. And they're looking at a new instrument that they got at the lab, new spectrometers that they were using for soil testing. But one of the things I thought was very interesting was in 1951, soil labs that blanket Illinois make 1/3 of all the U.S. soil tests. So Illinois is really kind of one of the centers for soil testing, for where it really started to get a hold and develop stuff. So do I have anybody here that's from out of the state? So everybody here is from Illinois, basically. So you can feel pretty proud that when we're talking about soil testing, a lot of the developments in soil testing are Illinois-centric. I mean, has been a lot of work done here. Even when I look at worldwide, if you look at places, other places in the world, they look towards the U.S. and they look towards Illinois for soil testing, have in the past at least. So, but that 1951 paper, this is the second page of it that talks more about some of the things that they're doing, and they're doing trace element studies, and it talks about why we have so many soil testing labs in Illinois, and it's because the university thought that was important, and so they went out and trained people to have soil testing labs, and we have a huge legacy of that in Illinois, and this is one of the men that really contributed to that over time. I think we had close to, at one time, I had heard that we had close to 100 soil testing labs in Illinois. We still have a fairly good concentration of soil testing labs in Illinois. It's not 100, but we have quite a bit. But Dr. Peck was a leading figure in soil science at U of I. He really advocated for soil testing, and he worked with a lot of different labs to promote soil testing, train people how to do the soil testing. So he has quite a legacy. And one of his things that he did was he helped maintain these archives at the University of Illinois that have all these old soil tests that came from all around the state. They came from the Morrill plots. They came from the whole series of plots. And I'll show you how many sites we had around the state where we were doing soil fertility experiments in the 1920s. But this is Ted Peck, and he's at GMS lab in Cropsey. That's Georgia Steffen, and she's just recently retired. But he was there, he worked with them very closely over time. So now we're getting more into this modern era of what are we doing now in soil testing. So we see in 45, Bray Kurtz developed the P1. Dr. Olson, Sterling Olson, he developed a test that worked better in high pH soils. So out west we have higher pH soils, so that works there. He developed that, and that's still a test that's widely used. 1950s, they developed at Cornell and USDA, they developed using ammonium acetate to measure potassium in soils, and that's still a widely used test. Then we go down to Dr. Malik, and he developed extractants. He was looking for universal extractants. He didn't want just either Bray or Olson And then ammonium acid, the separate ones, he was wanting ones that would do all the nutrients. And that's what he started developing. And he developed Malic 1 and 2, and then Malic 3, which is widely used now. Micronutrients, there's been work done on that. It's in the 70s, so we're looking at DPA for micronutrients. We still don't do a really good job on micronutrients, being able to analyze for those. So there's a lot of room for improvement there. Then in the 2000s, now we're getting into the era where we're looking at soil health testing and how that works. But I talked about what Dr. Bray said, that the extracted amount must be correlated with crop growth and under various conditions. And I said, well, what are those various conditions? Is it tillage, row width, population? And one of the things that comes out is you really should adjust your soil test calibration for your production system. And so so where do our calibrations come from? What's the production system that we were looking at when they made the recommendations? Well, here's the kind of the current recommendation system we have. Here's our recommendation system from the first agronomy handbook, which is 1967. So it hasn't really changed much since the 60s. We're still kind of recommending the same things. Here's the network in 1926. These were all the experimental fields where they were doing soil fertility research in Illinois. A lot of sites. A lot of these sites were donated by the community to do this research. So it was a great network. Here's an example of one of those sites, and the fertility research that they were doing. They had, lime, manure, residue. Their K product was Cannet, and some of these trials they were using rock phosphate for the trials. 1950s, a lot of the seed that the trials they were planting, very low population, that the soil was, they were planted 3 or 4 seeds on a hill, 38 to 42 inch spacings. So this is, the corn was over here, that's that kind of population. It was planted with a planter that looked like that. And then they cultivated it, used sometimes both ways so they get all the weeds out. Here's a good view of a little in the 1940s. You can see they could cultivate it that way or at an angle. So you could really go through and get the weeds out. Populations in the 1950s. This is an example, so we're looking at 9,000 to 12,000 plants per acre maybe. So here's Roger Bray was the one that had done a lot of the work with these sites. He's the ones that I came out with a lot of these recommendations that we're using today. So this is some of his data from the 1930s, and you can see how the lines on our current agronomy handbook are very similar to that. So either nothing has changed or we're still using some of that old data in what we're doing. And I think it's that's up to debate a little bit, but I think that it's time to go through and update those recommendations, look at our current farming practices, our current farming systems, and update them for the conditions we have now. So, and how's that going to change things? I don't know. That's a question for Dr. Jones to answer and the people at the university. But I think they will change, and I think we have opportunity to improve how we manage nitrogen. So I think I'm about out of time. So.
All right, let's say thank you to Tim Smith.